this short section, we'll investigate the phenomenon called the Hall effect. And the Hall effect is important in the laboratory or in the fab because it allows us to measure whether the doping in a semiconductor is N-type or P-type, and then also to determine the actual number of carriers, the doping density. So the Hall effect occurs when current is flowed in a semiconductor in the presence of a magnetic field. And we have to revisit our kinematics of electrons slightly for this discussion. So the geometry is like this. We impose a current flowing in one direction, and then in an orthogonal direction, we impose a magnetic field. Now the force on a charge carrier is composed of a component caused by the E field, which we've already discussed, but also there's a component that's due to the magnetic field, and it's a little more complicated because it's the velocity of the charge carrier across the B field. So if we have a hole carrying the current inside the semiconductor, so the semiconductor is P-type, we can use this as our positive test charge. The hole carrier is moving in this direction with its velocity along my index finger. The B field is my thumb, and thus the force must be pushing this hole to this side. Now, the conventional current is actually opposite to the direction of electron flow, and so if I consider an electron, what I'll conclude is that the right-hand rule tells me the velocity is going this way, the B field's that way, so the force is this way, but we have to remember that that's actually for a positive charge, and thus for an electron, we have to turn it on its side. So again, an electron would go to the same side of this slab, be pushed towards the far back of this. So then if we consider that this is going to cause sort of a accumulation of either holes if it's P-type or electrons if it's N-type, we'll actually build up a voltage across this slab. So we can consider this side to be grounded, and then we have our voltmeter measuring between the ground and this other face over here. So the sign then of this Hall voltage which appears tells us whether our material is N-type or P-type. And the magnitude of the Hall voltage can tell us about how many there are per cubic centimeter. So what we have to seek now is the steady state solution. And we're going to need to introduce a few geometrical parameters. So we're going to say this is the length, L, this is the thickness, and this is the width. Our current density, J, is going to be I over the width times the thickness. And this is also going to equal the electron charge times the velocity of the carrier times the number density per cubic centimeter. So solving for the velocity, we can move these over here and get that our velocity is equal to our current over WT times EN. Now we're going to, as I said, seek a steady state solution. In steady state, the two forces here are going to be balanced. And the force I'm talking about is actually arising from the E field set up by the Hall voltage. So this E field for holes would point in this direction. And this would be opposing the Lorentz force, which is this term. So if we look at this geometry, the Hall voltage applied over the width equals our E here. So setting these two terms equal, we have that by magnitudes, E is EV B. Because all of these quantities are in orthogonal directions, we can drop signs and cancel these, and then substitute in here. We end up with E Hall, which we're going to rewrite as V over the width, is equal to the current times B over width, thickness, E, N. Widths cancel, and we're left with V Hall equals IB over EN. Now we can make this equation look something like Ohm's law, which is V equals IR, by defining these quantities here as R Hall. So we write an analogous equation to Ohm's law, which says that V Hall equals, oh, excuse me, I included the magnetic field when I shouldn't have, is going to be your current times your magnetic field times 1 over the thickness, E, times N. And the sign, as we said before, is going to be plus or minus, depending on whether your charge carriers are holes or electrons. So this is a great experimental way to measure the concentration and carrier type inside a piece of semiconductor. But in these days, it's also used very effectively to make magnetic sensors. And every one of us who has a smartphone that has a compass built in actually has one of these Hall sensors in our pockets. So, but you can actually consider this Hall sensor to be a mobile version of this experiment where the B field is actually the Earth's field. And the goal, if you're making magnetic sensors, is to have a very sensitive response. And so you want to be able to measure a large voltage. To measure a large voltage, that means you actually need low doping over here. So Hall sensors are built from lightly doped, high mobility semiconductors and can detect the small magnetic field from the Earth's built-in field. So now let's look at two more aspects having to do with the Hall effect. The first is the use of the Hall effect to determine the mobility. But you need to combine two experiments, actually. You need to combine a measurement of the resistivity along with a measurement of the Hall effect voltage. So we'll return to our same chunk of semiconductor, and to do a resistance or resistivity measurement, we measure the voltage from the ends through which the current is flowing instead of the transverse voltage, which we measured for the Hall effect. So we'll use the same geometric parameters. And to determine the resistivity or conductivity, we'll remember that 1 over the conductivity is the resistivity, that the resistance is rho times L over the cross-sectional area, which in this case is W times T. And then we'll use Ohm's law to determine our resistivity and then solve for the conductivity. So the conductivity in total, if you have a system that has both electrons and holes, would be N mu N plus P mu P. So the mobility of electrons and of holes appears in this equation. So for the general case, you would have to keep both of these. But let's make the approximation that our material is N-type doped, in which case this part of the conductivity drops out. So if we know our sigma, we know then that E and mu is our conductivity. And then if we know our N from our Hall effect experiment, we can figure out our mu sub n by measuring this plus V Hall. So putting it all together, we can, with one simple experimental setup, we can determine the most important transport properties of the material, the number of carriers per cubic centimeter and their mobility.